All right, welcome. This is lecture 2 in week 3, and the topic is classification. So to start, I just wanted to flick back to where we left off, or a little before where we left off last time. And the idea here is that we are trying to derive a very basic, simple version of a linear classification model. And in fact, there's still no learning as such. We're going to get onto that just after this. So the idea is, as we said last time, we have two clusters, if you like, of positive and negative examples, and we find the mean, the centroid, the mean vector for both of those. The mean of the positives is the vector p, the mean of the negatives is the vector n. Now, they are linearly separable here. We're going to, basically for this, the rest of this class, we essentially assume linear separability up to the last method we look at. Okay, now, what we said was the actual classifier is just a linear model with a threshold. So W transpose X, or W dot X, is the threshold. We can use homogeneous coordinates, and we can have the threshold as actually a parameter that we can learn as well, and then W dot X is going to be equal to 0. And in the framework that we're going to use, we're going to set W to P minus N, and in order to sort of maximize the distance between the two centroids, we're going to take the halfway point, and we're just going to, divide by 2. And then the model we're going to get, which is the one I showed on the slide, is the threshold will be equal to this expression here, squared Euclidean norm p minus squared Euclidean norm n, where those are the two centroids, and take the average, divide by 2. So where does this come from? So that's where I want to pick up on now, and I won't take too long. So this is we looked at this last time. This is the idea about the geometry of such classifiers. So if you're just not sure about that, go back and have a look at this. And this is the derivation of that classifier. So this is essentially the same picture that we just looked at. I've just changed the setup a little so that it's centered around the origin. But here is our cluster of positives, and here's the centroid, this red dot in the middle. Obviously, we're in 2D. This is well, let me just label the axes. This is x1, this is x2, so we're in 2 space. The other centroid is down here. We label it n, and you can see that there is a nice big gap between the positives and negatives, fortuitously. So the work through is just what I've written here. Just in the interest of time today, I've got quite a lot to get through, so I'm not going to, I wrote this down before. So I'll go through it quickly. If you're not sure, take it to your tutor. Think about it, work through it. If you're still not sure, ask your tutors about it. So W is, as we said, going to be P minus N. The decision boundary, we're doing linear models for classification, so this is just what we said as well. And we take the midpoint for the same reason, to try and maximize the distance from the threshold to each of the centers of the two classes. And because they're linearly separable, that it'll definitely work. And in some sense, this is good. We'll later in the course make this more precise, this idea of having a good separating line or plane or hyperplane. But for now, let's just do it this way. So we know that this is our setting. W transpose X is T. Now, if we have an X that is equal to this, then it must be on the threshold, right? That's what we're saying. We're defining that as a requirement. So then what we need to do is find a solution for W transpose X given the setup. Now I'm not going to work through it like this, but on the previous slide, this is what we said it was going to look like, and you just go through the steps. Essentially, you expand these two things out, and then these are common terms in the middle, and you end up with this, and rewritten in the form of the Euclidean norm, it gives you the thing that we wanted at the outset. So that is how we get that simple classifier that we said we wanted. Okay, now let's do, so that kind of finishes all the reasoning we did about the geometry of these simple linear classifiers last time. Now I want to do a bit of a digression in a more practical kind of direction for two reasons. One is it's important to make clear when, so we haven't really talked about learning yet, but for classification, when we're learning, we do need loss functions, and we need to evaluate the models. So this is just a little bit of a warm-up. So the setting is not the same as regression, but it's very similar. So we have labeled data. So it's written here X, so we assume X, I mean X could be a vector or it could be a single value, but, and then C of X. Now, this is our idea about the framework where there's some data generating mechanism, as we said last time. It's, for regression, we just said, oh, it's a linear, you know, it's a linear model, it's a function. Here we're saying it's a classification function, C for classification. And again, we don't know exactly what that is, that thing we're trying to learn, but we do have data on examples of the thing we're trying to learn. And our job is to come up with a model of some kind, could even be this very simple model that we derived before, and that will give us, for every X that we put into that model, such a model would be W transpose X, you know, just as we derived, will give us a classification. And we call that C hat, just as we did before. Now, the very simplest sort of classical evaluation metric is accuracy, ACC, accuracy. And we imagine we've got a test set, right? I mean, when we're learning, we use accuracy on the training data, but in general, to evaluate, we're interested in a test or eval set of some kind. And it's just the difference between what the predictions are for each example and the labels, and then we sum them up. And then to get an average, we divide by the size of the data set, test set in this case. And I here is just a fancy way of putting this in mathematical form. It's just the indicator function, which is 1. So it just counts the number of times you got the right label in your prediction, which is great. Now, for loss functions, usually take 1 minus the accuracy, and we call that error, because we want to minimize error. So it's just very straightforward. However, there are some things that are worth noting. For example, the errors are identical whether or not, so let's assume, I didn't say anything about what the classifications were here, right? They're just outputs, C hat versus C. Outputs of the model versus labels. Okay, fine. But what we may be interested in is some sort of finer grain information about where classification gets it right and where it doesn't get it right. And this starts to get fairly involved, particularly when you have multiple possible labels. Like these days, it's very common to see data sets with hundreds of thousands of labels, if not more. And then the question is, well, you know, are there any differences between, you know, I mean, obviously if we predict the correct label, we're usually fine with that. But if we predict the incorrect label, we might be wanting to sort of debug our training and say, okay, why did it get that label when it should have got this, this label? Why did it predict that class when it should have predicted this class? Now, to get fully into that is beyond the scope of what we're doing in this course. There's lots of information available about that. And for various applications, you'll need to get into those more complicated metrics. But to kind of set the scene a bit, I just wanted to briefly look at just the setting even when we have two classes. And you've probably seen something like this before, but this is variously called a contingency table or a confusion matrix. And it just lines up, in the case of two classes, the actual labels, and there's two choices obviously, and I've called them yes and no, just to keep things different in the labeling versus the metric. So you have data and can have either of these labels, and then your model obviously needs to predict out of the same set. So it could be predicting yes, it could be predicting no, and obviously you want to be on this diagonal. So when the class is yes, you want to be predicting yes. When the class is no, you want to be predicting no. But these are called true positives and true negatives respectively, but off the diagonal, you can see the two sort of error cases, right? So even in this simple setting, you might be interested to try and debug your learning method in terms of, oh, what kinds of errors am I getting? Am I getting false negatives predominantly? Am I getting false positives predominantly? The reason is that you may, that may give you some insight into where the model's going wrong. Furthermore, in applications, it may be the case that you need to take care of one type of error more than the other type because they have differential costs. Now again, this is a big topic that is out with the scope of what we're doing here, but it's worth noting that you may achieve low error, right? So you may be getting low numbers for error, but if the costs of making, let's say, a false negative versus a false positive are different, and you, let's say, false positives are more costly than false negatives are more costly than false positives, then clearly you would like to pay attention to that and try and minimize false negatives, possibly at the expense of making more false positives, but then the overall cost may still be worth it. Okay, and even for the case where you're not getting an error, like you're getting it correct, you know, there may be more value or benefit in predicting true positives versus true negatives. And that typically happens when the class distribution, so even in a two-class problem, the class distribution is just the ratio of positives to negatives. And it's very typical, or it's quite typical, to see data sets where that distribution is very, very skewed. And there can be very straightforward reasons for that, because it may be very difficult to get examples of one or other of the classes. So, for example, the thing you're trying to learn a model to predict, the positive thing, there may be very, very few of those examples that you can get. So the positive class is very small relative to the negative class. So that kind of imbalanced class ratio is something you need to pay attention to. So it's not simply that the job of the machine learning engineer, which is you, is to minimize error. You might need to go beyond that and think, well, what types of error are being made and how do we handle that? And yeah, so obviously the size of the data set is n, and that breaks down into the sum of these errors. Now, it turns out, and I don't want to spend too much time on this, but I just wanted to draw it to your attention. It turns out that in many applications, so this is really on the applied side, which is, I think, something I want to stress, although we do a lot of theory. Obviously, at some point, we need to engineer this theory into solutions and applications. So we can, here's a condensed version of that table. And we can just now think about the relationship of these true positives, true negatives, false positives, false negatives. What do I mean by that? Well, we can start to look at what's sometimes called the marginals, right? So we can say the predictions, the things that are predicted, are the true positives and the false positives. So now we're trying to say, we're trying to predict positive, right? If you think about, the reason I'm emphasizing this is if you think about the linear classifier, we typically are thinking in terms of predicting the positive class, right? So we threshold our little linear model, and we say, okay, if it's above this threshold, then it's positive, otherwise it's negative. Okay, so the key point is to try and find that threshold where you're predicting positive, hopefully without too many errors. All right, so that would be the number of predictions, the number predicted positive implicitly, and then the false negatives plus the true negatives are the numbers that are in some sense not predicted. Now, I want to emphasize that this n pred and n not pred, this is just me, these are not standard things. I'm just trying to draw this to your attention in a unified way. There is some material out there on this, but I don't think anyone uses these abbreviations. So if you go to someone and say n pred and they look at you, you just say, don't worry, it was that crazy guy who told me about it. This is what it means. Okay, so, and similarly, in terms of the actual classes, I'm saying, well, if you look at the true positives and the false negatives, what are they? Well, they are the actual labels. That is the, so this number here, these are these marginals, right? So n pos would be over here. And then n neg, so the n pos is the number that are actually yes, and n pos is the number that are actually false. Okay, so I'm just summing the columns, calling them n pred, n not pred, and I'm summing the rows, calling them n pos, n neg. Now, why am I doing that? Well, you can basically start to come up with various formulations that may be useful in analyzing the error of whatever classifier you're looking at. And this could be something you've done by hand, or it could be a machine learned thing, whatever. Probabilistic model, statistical test, whatever it might be. Now, I'm not going to get into this in detail, but the reason I did this is I wanted to get on one slide some common metrics that get used in different domains, and I've given them their names over here. And this is not an exhaustive list, but I just wanted to show you that there are different ways that you can evaluate the output of classification. And on the left-hand column, I've expressed them as conditional probabilities, which again is not standard, right? But I've just done this to try and capture, you do see this sometimes, but not in the way I've done it here. So this is just saying the probability of making, of predicting, let's see, n pred, this is the, making a prediction of yes, given that the data is actually classified yes, is this. Number predicted, yes, given that it is actually yes, is this expression here, true positives over true positives plus false negatives. Check, when you're reading this back later, check to see that that makes sense. Now, this is actually, the first one is actually a very commonly used metric. In machine learning and information retrieval and some other places, its name is recall. In biomedical applications and other types of applications, people call it sensitivity, right? So if you go to a biologist and talk about recall, they'll look at you as if you're nuts. If then you say, oh, sensitivity, they'll say, okay, yeah, I know what you mean. Right, now I'm just raising this because these metrics, it's not all simply about error. That's the point I'm trying to get to, right? So these metrics are important. They come up in various applications. There are others here, but I'll just leave that for you to refer to later because I'll need to get on to our, excuse me, next topic. So the next topic is something I'm sure you're probably familiar with. This is now absolutely standard practice in machine learning evals. So the topic is cross-validation. The simplest training evaluation setup is to take your data and split it into two, not necessarily equally, commonly things like 60-40 or 2/3, 1/3, into training and test. And you train on the training data, obviously, and you test on the test data or the eval data. More commonly, these days, you would train, split it into three, or split it into two, and then split the training data further into two. And then you hold out the test set, the thing at the bottom, and you don't touch it until when you train on, you get to the point where you train on the training data and evaluate on the validation set or the val set, you think you can't do any better, and then you run on the test set. And the standard advice is to only do that once. Now, the sort of dirty secret is that, and this can catch you out, the dirty secret is that people, as soon as they look at the test set result, they say, oh, maybe we can do better by, trying something else. And then immediately, the value of the test set as a sort of independent estimate of the true error of your model goes away, right? So don't do that. And if you're wondering, you think I'm just making this up, this is a big problem because people release validation sets, they release data sets publicly, benchmark data sets, and people go and train and test on them all the time, and this is like an arms race to get the lowest error. In all probability, unless the benchmarks are really sort of held back, then you quickly get to the point of overfitting. I mean, it's a bit more subtle than that. If the benchmarks are really, really big, and you test and train you train and test on many different benchmarks, and the model looks really good, then you're probably okay. But you need to be careful. Really, the gold standard is someone releases a benchmark data set, you do your best on that, and then you go to them and say, now, here's my model, and they say, okay, and then they run it on a held out data set that you haven't seen, and they keep, and then they give you back your result, and they say, okay, didn't look quite as good. And this goes on in research, and that's what you should shoot for as a sort of the gold standard for evaluation. It doesn't mean that if you train and test on the benchmark that's open, and you hand over your model, it's not going to do really well on the test set, right? That can certainly happen, and then that's it. That's what you want. But that's methodologically the ideal way to do it. So that's why you see people issuing various challenges, and these days machine learning companies have a strong vested interest in trying to crack these gold standard things, and they do that often in competitions. You may have heard of some of them. Okay, and then one sort of further thing that you should always be doing is cross-validation on this, on the, you know, the training data. So cross-validation is I'm only showing threefold cross-validation here. You take your training data, you split it into three, you take 2/3 to train, and then 1/3 to validate, and then you repeat that in each, in three ways to use each of the partitions to test on independently. Furthermore, you should, as good practice, always randomize the data. You should check for things like class distribution, and you should try and approximate the true class distribution in the whole data set in each of these cross-validation folds. That's called stratified cross-validation. All this is in, you know, a lot of good information about this kind of methodology is in the public domain, but it's important to stick to it. Okay, so that was a just quick digression, because we talked a lot about, in the first 2 weeks, mean squared error and just minimizing mean squared error. With classification, the setup is a bit more nuanced, I would say, because you know, you could be predicting multiple classes, and there can be these different metrics that get used. And as you would have seen, mean squared error doesn't quite fit in to that setup. All right, so now we need to talk about a classic learning method for linear classifiers, and that is the famous perceptron, which is one of the earliest, not the earliest, but one of the earliest machine learning methods. Here's one of the guys. This is the person who invented the name. You can see there the name perceptron. If you look closely, you can actually see that this was a TV news broadcast. So there's nothing new about AI being in the news. This is whenever this was, I don't know, sometime a long time ago, like over 60 years ago. So AI hype comes around every so often. We're in a big wave at the moment, but it's not new. Okay, so the perceptron was designed to actually be implemented in hardware, was implemented in hardware. As the name suggests, it was designed to work on sensory input and basically classify objects and things like that. The implementation goes back even further to something called the McCulloch-Pitts neuron. And basically this approach is the foundation of all modern neural networks. Right, so it goes all the way back to there. Now, the model itself is just a linear classifier. And here it is in graph form. So here we're actually, for us, we know that this is homogeneous coordinates, because we have for every, so x is a vector of inputs. We've got n inputs here. We've got a bunch of weights. So this is the graph representation, because these guys were thinking of actual biological neurons. So they thought, okay, a neuron is a cell. It has input and output. So let's model a neuron having multiple inputs like this. And this is what they came up with. They have this offset, which is fixed at 1, and this also has a learnable weight. And then you sum all this up, so this is just our W transpose X. And the perceptron's threshold was just a hard threshold, just like we saw before. So for mathematical convenience, typically we have in the perceptron +1, -1 outputs for positive and negative. Okay, and because we're using homogeneous coordinates, it makes sense to threshold around 0. So just I just noticed that. Okay, that's interesting. I haven't noticed that before. I just noticed that I've put greater than or equal to 0 in the diagram, and I've put strictly greater than 0 in the formula. So I don't know why I did that, but I'll try and fix that for you. Okay, so yeah, in vector formulation, okay, I've done it again. That was not good. Okay, so perceptrons are linear models. They're based on this idea of a biological neuron with a hard threshold. Now, the key thing is that the perceptron, we'll get to the algorithm in a second. It's a very simple algorithm, but it has some nice properties, particularly if the problem is linearly separable, the perceptron can work. Now, in 2D, A is a linearly separable function, and B is not. So we can think of essentially linearly separable functions are linear threshold functions. And if you think in terms of Boolean functions, you need to have a number of the inputs being true in order to cross the threshold, and that implements the function correctly. And the two sort of classic examples of this are the OR function, where if at least one of the inputs is essentially positive, then you will cross the threshold. Or another way of saying that is only when none of the inputs are strong enough, you're going to cross the threshold. The AND function is you need all of the inputs to cross the threshold, otherwise it's false. And when the inputs are strictly binary, 0 and 1, obviously those are the familiar AND and OR functions. But they're really a general, they're both examples of this general idea. We need enough of the inputs that when summed together with their weights, we cross the threshold. That's the idea. So essentially the same kind of function. A different kind of function is the famous XOR function or parity function. Let's just stick with XOR. Now, the problem for linear models is that a single linear model will not be able to represent, let alone learn, the XOR function. And the reason for that is visible here in this diagram, that the is visible here in this diagram because it's not one of those simple linear crossing threshold functions, right? To sort of see that, you could imagine that for this guy, this particular point, which is plus 1, minus 1, minus 1 plus 1, or plus 1 minus 1, which is this other one here, you could imagine points and this point and points close to it being representable by a line that goes kind of like that. But the problem is you're always going to misclassify points in this quadrant, and vice versa. Okay? So the solution is what all modern neural networks do, which is to have multiple versions of perceptrons, put them together. You have to be a bit careful with what the connection weights are, but essentially you can solve the problem like that. Surprisingly, it took quite a long time for people to get to the point where they could do that. In fact, it took about 25 years for this problem to be solved. It was actually solved multiple times. And when we talk about neural network learning, we'll go through those steps and derive the solution, but that problem held people up with perceptrons for quite a long time. And there's a lot of nonsense talked about perceptrons. Essentially, the idea is perfectly fine. It's mathematically sound. You can even prove theorems about them, and everything's fine as long as you're happy with linear classifiers. If you're not, if you need nonlinear classifiers, more complicated functions, then you have to scale up the model. Not really controversial. Some people seem to seem to get very worked up about the whole thing. So go figure. All right. So as I said, if the function is not linearly separable, you're going to need something else, which is basically networks. And this is the whole start of deep networks, because this idea of requiring a more complicated architecture of perceptrons where you stack them side by side and then stack them layer by layer is essentially what deep learning is. There can be different sort of architectures for these kinds of things, but that's what is going on. So how do we learn a perceptron? Well, simply learning a good set of weights. We know it's a linear model. We know how to learn weights for linear models. We've seen it for regression. The perceptron algorithm is actually quite interesting, though. It's not exactly the same as the approach taken in linear regression. There's not an exact solution in the same way as there was for simple linear regression or even the simple linear classifier that we just did. But it is, so there's a sort of iterative algorithm that we'll get to, which is not exactly gradient descent, but it's very closely related to it effectively. But importantly, it is not gradient descent. So anyway, so we have weights, and the idea is that at every iteration of the algorithm, we need to update the weights based on some change in the data. Now, one interesting thing about the perceptron is that it is what's called, or sometimes called, a mistake-driven learning algorithm. It only actually makes an update when its prediction is different from the label of the example. And the strategy it uses in learning is also quite interesting. It's called, or at least in the version that I'm going to show you, it's called prequential learning. You don't have to remember that term. It's a term from statistics. But it simply means I see, I'm given an example, I have a model, I make a prediction, and then I'm shown what the label is, right? So if you think back to week 1, lecture 1, I said, you know, we need to think about prediction and learning as sort of two sides of the same coin. So in the humble perceptron, that's simply what we're doing. We're saying, okay, we have a model at some point. Initially, it has no information in it. We make a prediction. We get some feedback. We do an update, and we keep going like that. So this is actually a very powerful and general framework. It's essentially the same framework that is used in reinforcement learning, which I don't talk about in this course, just for reasons of time. But it's the same sort of setup. Have a model, make a prediction, get some feedback. If the prediction was wrong, change the model. And this relates to things like Bayesian learning, which I'm going to be talking about in a minute as well. Okay, so that's a lot of setup. Oh, there's also a learning rate or smoothing parameter. I'm typically going to not really talk much about the learning rate. In fact, in the derivation, I'm going to basically ignore it. And one interesting property is that you can prove that the perceptron training algorithm I'm going to show you will converge if the data is linearly separable. And it says here if eta, the learning rate, is sufficiently small. In fact, usually you prove it totally ignoring the learning rate, and that works as well. Okay, so let's just do the setup, and that'll take us to the break, I think. So the setup is pretty simple, and there's a bit of reasoning behind it. So let me just go through it. And let's see. Okay, so let's say we've got a vector xi. This is a bit of data. And let's say it's a positive example, but the algorithm that we have, which runs the model, gets it wrong. So xi is misclassified. What does that mean in practice? Well, it means that the true label yi is +1, but the model w.xi is less than the threshold. Okay? So here we're using implicitly, it's classified positive if it's greater than or equal to the threshold. All right, but it's less than the threshold. So what we need to do is change W to W prime, some W prime, and we need to have the W prime with the example, W prime dot xi, is greater than W dot xi, because W dot xi is wrong, it's less than the threshold. We need to make it bigger. This W prime must be bigger than W, sorry, let me just be correct. We must find a W prime such that when dotted with xi, that dot product, that scalar value, is greater than W dot xi, which got it wrong. Now, we're not guaranteeing that W dot xi will get it right. We're just saying we want it to be closer to the solution. I mean, hopefully we do get it right, but we're not going to try and get there all at once. But we will. This will have the effect of moving the decision boundary towards xi. How do we do that? Well, we can do that as like this. We can add xi to the weight vector. We can also modulate that addition by the learning rate, this rate parameter eta. Now, typically, as I said, eta can be anything. Well, often it's not that large. I mean, it depends. We talked about learning rate before, right, when we talked about gradient descent. This is not gradient descent, but we're also using eta for the same kind of idea. We don't want to make steps that are too large because that might be unstable in the learning. I'm hand-waving a lot here, but I can tell you that you can actually just set eta to 1 and not worry about it, at least in this formal setting. A quote-unquote good value of the learning rate in machine learning is nearly always set empirically. There are some theoretical ways in which you can sort of supposedly derive an optimal learning rate, but in practice it's something that you would determine empirically. So I'm really not going to worry about it. In fact, I'm usually going to assume in today's presentation that it's simply 1. Right, so assume it's set to 1. So then we have that W dot xi is W dot xi, the previous model, plus xi dot xi, okay? Because we are adding this to this. And clearly that is going to be greater than W dot xi. But basically the way to think about it is we're just adding the data to the weight vector. And we know that they are the same dimensions, so it's just a, an addition, vector addition, modulated by the learning rate. So this is the key idea. We need to make W dot xi into a new weight vector that gives a larger value for the scalar product. Because it was a positive example, so the scalar product should have been above the threshold, but it was not. It was below the threshold, so we need to push it closer to the threshold. That's the idea. Or actually change the threshold. And the same argument essentially applies in the other direction. If it's a negative example and we get it wrong, the model gets it wrong, that means that the label was -1 and W dot x, okay, I'm using xj here just to keep the two things separate for the time being. So xj is an example bit of data that should have been predicted negative. Its label is -1, but W dot xj is above the threshold. Okay, so the new weight vector is going to be, we subtract the bit of data, or the bit of data modulated by the learning rate. But here we're just subtracting the bit of data from the weight vector. So again, just vector addition. And then we're going to get this, a new weight vector W prime. Now, if we look at this expression, it's almost exactly the same as this expression. So here we wanted to make it the new thing W prime dot x, which is expanded to this, given how we're going to do the update. which is going to be greater than this dot product. And we're simply adding the data, right? Here we want it to be less, and we're subtracting the data. So if you look at this expression, the only thing that changes is the sign, right? Plus eta xi dot xi minus eta xj dot xj. So we can combine these into a single expression, which gives us this update rule. Okay, and now we're using the fact that the labels are +1 or -1, so we're just using them like to have the correct sign. So the update rule becomes very simple. It becomes the existing weight vector plus the data point xi, and we're back to just indexing into I, so I is one of our training data points, times the label, right? So that'll change that either as into -xi or +xi. And that corresponds to the sign inversion of the misclassification. And because we only do this when we get it wrong, then the weight vector moves in the right direction each time, right? It's either plus or minus, given that we got it to below the threshold or above the threshold incorrectly. And the weight vector will not change if we got it correct. I mean, you know, if it ain't broke, don't fix it. So as it so yi acts to change the sign of the update, as we just said. And this is the basis of the perceptron training algorithm. And the algorithm as such has this prequential form. It was originally sort of, well, you can think of it in two ways. You can either think of it as data comes in a stream. You look at the data point, you make a prediction, you check the label. If it's wrong, you make an update. If it's right, everything's fine. Or you can think of it as, well, I'm given a bunch of data, and then I run through the data iteratively. Each time I check to see whether my model's okay, or if I need to make an update, right? It really doesn't matter. But the streaming thing is kind of nice if actually streaming, you really do have streaming data. I mean, obviously you don't use perceptrons these days, but that framework is a useful thing to think about in terms of if you do have a streaming data problem. All right, so here's the algorithm. The setup is pretty much what we said. We've got training data in homogeneous coordinates. That means we can look at thresholding around 0. We have some learning rate. And then the thing that we learn, the model as such, is just the weight vector. And we're just going to take the sign, or in other words, okay, you've always got to be careful around 0. It could be strictly greater than 0, so strictly positive, or it could be non-negative, so greater than or equal to 0. You know, if we take the sign, depending on how sign is defined, you're going to get the same thing. Now, you can initialize it in different ways. The simplest version is just to initialize the weight vector to the vector all zeros. It's an iterative algorithm, so at some point you're going to decide whether you've converged. So we haven't converged, and then as long as we haven't converged, we say, okay, maybe we will converge on this iteration, and then we run through actually that's not, I should say epoch, right? So epoch is neural network speak for one run through a bunch of data. And then each iteration is, we take for every data point, every x, y pair, we go through and we check. We say, is y times w dot xi less than or equal to 0? This is the criterion for misclassification, because if y is positive and w dot xi is positive, above the threshold, then this will not be true, right? Similarly, if yi is negative and w dot xi is also negative, that will be positive and this will not be true. So it's only the case when it's not positive that this is a mistake. And then we do the update. This is the update that we just derived. We worked out on the previous slides. And we obviously haven't converged. So we keep going. Okay, and we keep going until, I mean, again, you can have different criteria. So this assumes that the data are linearly separable, and as I said before, you can prove that the algorithm will converge if the data are linearly separable. If the data are not linearly separable, which in practice is quite likely, you would have to have a different convergence criterion, but that's essentially what we have. Okay. Any quick questions about that? Because we're coming up to the break. If there's no questions. Well, actually, let me leave you there. And on the recording, we'll be back in 10, and in the room, you can think about that and come back with some questions. Or you can just stand up and move around. It's Friday. It's nearly lunchtime. Right, get some fresh air. We'll be back in 10 minutes. Okay, let's resume. So I wanted to quickly show you something without proof. I may, if there's time, come back to this. So the perceptron training convergence is a classic theorem. It's the case that when the data is linearly separable with a weight vector that I'm calling W star, gamma, which is greater than 0, is something called the margin. Now the margin is, I've drawn a little diagram down at the bottom. So imagine our 2D space, and we have, let's say these are the positives and these are the negatives, and they are linearly separable. The margin is the gap between the line, which is defined by W star xi for all the xi, this is the gamma. So if you place the line so that it's equidistant between this point here and this point here, which is the nearest positive to the line and the nearest negative to the line, that's the margin. Okay, and there's this theorem called Novikov's theorem, which is done around the time that the perceptron came out, because there was a lot of excitement about AI, machine learning. What could it do? What couldn't it do? And so this theorem came out almost at the same time that the whole perceptron thing was being developed. And it said, yes, it will converge with, in a finite number of mistakes, given these conditions above. And that finite number of mistakes is bounded by the radius, which is simply the size of the largest xi, right? The magnitude of the largest xi, the norm of the xi, the largest xi, and this margin. So the way you should think about that, I think, is that if none of the examples, like the positive example and the negative example, if they're, really a long way away from all of the other examples, then if you think about it, the value as a coordinate of xi will be quite large, right? So that's kind of like how spread out the data are. Remember, they're linearly separable, but how spread out are they? And then the margin is, well, how easy is it to find a separating line, right? If the closest positive is very close to a good line separating them, then the margin is going to be small. And it's squared, but the key thing is how spread out is the data, and how good is that margin for this optimal solution. So we don't have time to go through the proof, but that hopefully will give you some intuition about what's going on. So then I have an example of the kind of thing that happens, and again, I'm not going to go into this in too much detail. In fact, maybe I should show you on this, because I can zoom in a bit. You can read this for yourselves, but the key idea is that the learning algorithm, I'll just show you this one example. This is about learning rate and the effect of the learning rate. That's what this figure is about. But I just want to give you an intuition. All of the action is really about how, so these are the positives and these are the negatives. All of the action is how difficult it's to find that separating line, and it's all really about the points closest on either side of the line. And the mistakes are going to be made, as you can see here, these dotted lines are estimates of the weight vector, and they make some errors. Like, for example, a line over here is going to make the error that it'll predict this positive example as a negative, right? So hopefully, intuitively, you can sort of see that the whole aim of the algorithm, and here the radius is not too big, but here the margin is actually quite small. It's quite tight, right? So that's really the difficulty of learning, that kind of stuff. Now, this is a very simple learning system, but hopefully this can give you some intuition as to where the actual learning problems are going to come in. Okay, right. I think that's enough on the perceptron. Let's ask this question. So you might say, well, you spent a lot of time talking about linear regression. Linear regression fits a line. Now you're telling us that linear classification, which is just, again, finding a line, is like a different thing. So why can't we use all the stuff you just told us about linear regression and use it to do linear classification? So the answer is yes and no. And what I mean by that is that there is an approach, I mean, there are approaches that do that, but they're not quite as straightforward as you might think. So here's one approach, and this is, again, related to things like neural learning and ensemble learning, which we'll get to later in later lectures. But one simple idea is for each class, for each class, we train a separate linear regression model. Okay, so I take my data set, and let's say I had 5 classes. I just find all of the examples that had class 1, and I could train the model as follows. I would set y for each example that was in class 1 to be 1, and I would set the other guys to be 0, and now I have a number for every data point in the data set in terms of predicting that class, and then I could train a linear model, regression, and then to do the prediction, I would take, if I had 5 classes, I would have 5 regression lines each model. I would push the example through, and I would get a value out at the end. And the simplest rule, decision rule, prediction rule would be predict the class with the largest output value for y. And something like this is very commonly done in neural networks with multiple outputs, each of which is essentially a linear regression. And you could do that. In various areas, this is called by the name multi-response linear regression. So it's not really linear regression. It doesn't, it's not the kind of thing that obeys the assumptions that we made when we were looking at linear regression. It's just a linear function of the data. And hopefully, if there's some pattern that is sort of linearly determinable for each of the classes out of the data, it might do something reasonable. And it's quick and it's efficient. Why more generally this could be a problem is that suppose the decision rule is we classify x as positive if some function of x is above a threshold, and arbitrarily we could say 0.5, otherwise it's negative. So if we wanted to use linear regression, we would say the function is a linear model, y equals a plus b x, and we fit that linear regression model to some training data. Now let's suppose that the negatives were labeled 0 and the positives were labeled like this. Just in the way we described before, this is kind of what would happen. You would fit a model. Let me try and pick some color. Right, so you'd fit a linear regression, and it might look something like this. Okay, it's kind of linear. And then the threshold would be about here. Right. And that would be a function. So this is we could call this f1, this function here, and this threshold. If the response, so if you push in an x, if you push an x into here, right? This is x. So for any x, just a univariate thing, you push it into the model, and it says, oh well, you know, it's less than 0.5. So if you're somewhere around here, it's less than 0.5, and therefore it's negative. That's good because these are labeled 0. Whereas up here, if you push it in, you're going to get a value around here, which is clearly above 0.5, and that would work. But the problem is if you have data that has a slightly different distribution, if you have a slightly extended distribution, if you get more data, you can end up with something like the following. You get a positive example for x way over here. It's okay, it's not sort of contradictory because you know, it's for larger values of x, it's y is positive. But the problem is if you fit a line like something like this using typical linear regression methods, sorry the line's a bit rough, but you get the idea. The threshold now is going to be rather different. The threshold of this line for being 0.5 is something like this. Not exactly, but reasonably close, right? And the problem here is that you're now going to classify these guys as incorrect. All right, so yeah, because these at this point on the second model, I mean, I haven't drawn the line that well. Let me actually. The bad drawing is kind of destroying my point. Let me try and really draw a line properly. This is why you need to be good at drawing, everyone. It's going to be something like that, right? Again, not great, but... Right, so the point is that for these guys here, which were previously classified as positive, they're going to be below the threshold. This guy is going to be correctly classified, but these guys are going to be below the threshold. Right, so it's actually difficult to get a good linear regression model for classification. All right. Yeah, sorry about the bad drawing, but hopefully the concept is clear. Are there any questions about this? It's not critical to know this, but it's just a sort of data point along the way about why do we need linear classification separately from linear regression? No? Okay, good. All right, so there is an approach to solve this kind of problem, and it's called logistic regression. And the name can be a bit confusing because it's related but not exactly the same, certainly not exactly the same as linear regression. What it is, or the setup that's usually done, and I'm showing you again the situation for binary classification, is that we have a model of this form. The model is a probabilistic model, and the model says the probability of y being positive, because it's a two-class model, it's actually going to be sufficient that we just learn in the positive direction. Is this thing here, and this thing here is one of these S-shaped curves. Okay, and you can see that tucked away in here, tucked away into this exponential, this negative exponent, is our familiar linear model. Okay, so it is learning, we need to learn a linear model but actually the model form is nonlinear. And one nice thing about this is it's sort of what are called squashing properties. So it kind of can squash data in the form of these positive x's and negative x's into this kind of thing. And it will actually not suffer from the problem that I showed you just a minute ago, because there I was forcing a linear model, just a linear model. This is now a nonlinear model that is you can think of it as a function on top of, or a function of, a linear model. And the function has this particular form, right? And in fact, again, if you're interested in neural networks, this is exactly the kind of, I mean, not exactly this function, but this kind of function is the type of thing that is used for classification outputs on a neural network rather than regression outputs, okay? So let's set this up. And then, depending on the time, I'll do a derivation. I may not have time, but I'll write it up for you afterwards. Okay, so if we model the probability of being in a positive class, so an instance being predicted positive, like this, we'll say probability y equals 1 given x is this thing here, okay? This is what we had on the previous slide. Now the alternative, because there are only two classes, must be 1 minus this. So 1 minus p, the probability of y equals 1. Okay, and it turns out that if we take the log of this thing, I mentioned this in last week's lecture. This thing, if we think of this as p, the alternative being 1 minus p, the ratio of p to 1 minus p, we called that last week, we called that the odds. And if we take the log of that expression, we release the linear model out of that thing. And this thing on the left-hand side is a logit. You may have heard of logits. They are essentially classification probabilities for a particular output. For example, if you use a language model, large language model, the outputs on the vocabulary of the model, the token vocabulary of the model are expressed, the values of them are expressed in logits, and if you want, you can usually via the API get the logits. So what we're doing here is we're defining a linear model for the logit. Obviously, with a large language model, it's incredibly complicated. It's an incredibly complicated model, but the probabilistic form is the same. All right, so let us look into, just for the linear model, how we might do this. So how we might do this is, well, we might say, maybe there's a solution. Unfortunately, like an exact solution for linear regression. Unfortunately, the answer to that is no. So what do we do when there's no exact solution? How do we train something? How did we do it for linear regression? We're in the framework of maximum likelihood. What do we do? Well, in week 1, I showed you that there was an exact solution for linear regression. And then in week 2, I said, well, imagine there wasn't an exact solution for linear regression. We can still learn linear regression. How did we do it? It was only a week ago. I know life is moving fast, but yeah. Yeah, but what was the algorithm? Gradient descent, exactly, that's right. So we want to minimize the loss function. For linear regression, we can actually just derive that solution, but we said, suppose you couldn't get an exact derivation, you'd use gradient descent, right? And that's the case here. We really can't have an exact solution. So we have to use gradient descent. However, so in your practical work, you're going to be looking at a version that actually is really gradient descent. But I thought it might be interesting to derive a method where you use gradient ascent, just to show you there's nothing special about gradient descent, because here we're trying to maximize the likelihood, right? So in practice, you do use gradient descent just because we've got all these algorithms and implementations. But to do the derivation, I thought I'd show you the gradient ascent version. But it's going to be essentially the same. We want to maximize the log likelihood. So we set it up like this. We have a conditional, okay, so the log likelihood, let's go back. It's going to be based on this, right? So here's the this thing here, this probability, and we want to maximize to find the weights. So the log likelihood, or the conditional log likelihood, because it's conditioned on x, is the log of the probability that given of 1 being positive, given x for some data point, times the label, plus 1 minus y times this thing here. Okay, so you might be thinking, where does that come from? But I mean, otherwise it's just what we saw before. Over a bunch of examples, we want to maximize this expression. So if you think gradient descent was minimizing, here we're just maximizing. And you can turn this into gradient descent, as we know, just by doing the negative log, conditional log likelihood. Now, there is a bit of a trick here. So just like the perceptron trick, we used labels to help us simplify the solution. Here we're using labels, and back then we had labels as +1, -1, so just as a sign. Here we're using them just as 0 or 1. And the advantage of that is that it'll make things easier to handle, because when things are 0, we don't have to deal with them. And we're dealing with y as 1 or 0, and 1 minus y as 1 or 0. So that's gonna help. Okay, now it's a little bit involved, but I'll go quite quickly. So I'm going to skip some of the things I was going to talk about. Let me just write the sort of first key idea. We're going to use the principle of conditional maximum likelihood. And there's a bit of a story behind this that I'm going to skip. So I'm just going to say, according to this principle, we're going to select some w hat, the thing we need to learn, because we know that's the form of our model, which is going to be argmax. So find a w that is a maximizer for the product of all of the data points. I'm going to use little n. I think I use big N in the slides, but we'll just write it like this, which is the probability of yi given xi parameterized by w. Okay, so w is the data's fixed, the y's and the x's are fixed. This expression says, okay, go off and find a w that maximizes, that's the argument to this expression that maximizes this thing, right? Which is just a product of all the probabilities. And I'm going to skip the justification, and then I'm going to write that for logistic regression, we need, or we're going to use this expression, probability y, which is the class, 1 or 0, x parameterized by w is going to be expressed by the logistic expression that we had before, 1 plus e to the minus w transpose x. Okay, so this is starting to look like something we can probably work with, right? Let me just draw a quick picture of what's going to be the result in terms of the sigmoid, right? So we've got so it's going to be 1.5. So the thing we're going to want is this function here, which is sort of not a great sigmoid, but you kind of get the idea. Now, sort of contrast that with the perceptron, right? So the perceptron function would have looked like, for the same setup, would have looked like this. The axes are a bit off, but perceptron is, you could make the perceptron around, let's say this is 0, right? This is 0. You could make the perceptron around 0, 1 as well. We did it -1, +1, but you can make it quite easily around 1. And then this would look like, this is just like this, right? Right, so this is the, that's not a great drawing, but you get the idea. This is the perceptron versus the sigmoid or logistic function. So both of them are linear models. On the left, you're doing a hard threshold. On the right, you're doing a soft or a squished threshold. All right, now let's do some setup. So P, so we'll let P be this expression, just shorthand. P, because it's going to get complicated, is y, x, parameterized by w. And we're going to say that that is the function. So predicting positive, if you like, 1 plus e to the minus w transpose x. And then we can say, well, 1 minus p equals, and I'm not going to go through the steps, so you're just going to have to check for yourselves. Omar has a nice video that I'll link to where he derives the negative log likelihood for gradient descent, which is actually a bit more straightforward. But I'll do it this way, plus e to the minus w transpose x. Okay, cool. Now, let me write down this. I'm just writing stuff down. You're going to have to think through it for yourselves. 1p over 1 minus p is going to be this. 1 e to the minus w transpose x. And then if I take the log of this, we'll just assume natural logs, but to avoid picking a base. So 1 minus p is going to be w transpose x. Okay, so if you look at this, if you work through this, you should be okay. So just to be clear, we're going to say that we're going to assume that x is in X is in some space, R, I could call it R P, but I'll use RD because we've got P already and I don't want to get confused. Right, so just at some dimensional space, Y will be in set 0, 1. And then, because we're going to need to expand on this, we'll say that log P1 over P is W0. Sorry, I think this should be the interval. 0, 1. Open interval 0, 1. No, sorry, it should be the closed interval. 0, 1. Log P is going to be, so we say it's like this, right? Just our expanded dot product form. So J goes from 1 to D, and W, J, X, J. So the components of the vector. All right, so the approach is going to be that the algorithm as such, which we're going to need to have, is that the algorithm is going to be gradient ascent. So we're going to initialize the parameters as usual. So we need parameters W0 to WD. Okay, and we need to compute the gradient of the log conditional likelihood. The log conditional likelihood. And then we will update the parameters. So this is logistic regression by gradient ascent. And then we'll update the parameters in the direction of the gradient. Because remember, the gradient, we usually take the negative of the gradient. But here, because we are ascending the gradient, the direction of the gradient. Okay, so it'll look like this, something like this at least. We have a function of the log conditional likelihood. Now, I'm going to draw it like this, and this is actually correct, but I'm not going to go into the convexity of the concavity of it all. Let's say that's the gradient. This is the log conditional likelihood, the LCL, which we're going to derive. And so gradient descent is, you know, if we're at some particular point, we have this vector, then, you know, gradient descent would send us in this direction up the hill. So this is a function of W. Okay, so that's the gradient descent idea. Just the same idea, and I just wanted to show you it as gradient ascent because okay, so the update rule will be WT plus. Okay, so let's assume a learning rate, eta. Now, what do we need to do? Well, we need the gradient, right? We need this, this thing here. So how do we find the gradient? How do we find the gradient? Partial derivatives, exactly. So we're going to say dW of this thing, the log conditional likelihood. So now we need to, sorry, I'm going quite quickly because I'm going to run out of time. In fact, in the interest of time, what I will do is this. I'll just write down the specification and then I'll have to fill it in afterwards before I upload the slides. So we'll say we need the gradient. Well, we know how to do that. We've done that before. Just need to find the vector of partial derivatives. Right, so it's going to be this. The vector of partial derivatives is the gradient. Sometimes I write it with that inverted triangle, but here we're just doing the partial derivatives. Right. Now, there is a sort of thing we can take advantage of that will appear when I write out the full derivation. Right, that's the thing we're going to need. Now there are a few steps, but basically we need to write down what the LCL is and then take the gradient. So I'm going to fill that in for you later, and then you're just going to have to trust me that what we get to is this expression, and I'll just write it down at the bottom. It's going to be for this, it's going to be sum I1 to n of yi minus pi, and you don't know yet what pi is, times xij. Okay, that's going to be the thing that will be derived. And then we simply plug that into, for each of these components of this. So this thing here, a lot of hand waving here, this thing here is going to end up being for each component, for each example, that thing there. So we can just plug that into this update algorithm and it will give us the gradient descent. Okay. All right. So yeah, sorry for not having time to do that, but I will upload that and you can get to that later. Now, I wanted to finish by just motivating maximum likelihood. And there's a bunch of things that I'm going to go through quite quickly, but they're pretty straightforward, and I believe you'll probably have seen things like this before. Okay, so maximum likelihood is a special case, as I said before, of Bayes' theorem. And in machine learning, we have models and data, and we just write Bayes' theorem like this. The probability of the model given the data is equal to the probability of the data given the model, the probability of the model, and the probability of the data. I talked about this last time, so it's nothing new. When we're talking about choosing a model, there are different approaches. One well-known approach is called maximum a posteriori hypothesis selection, or model selection, which is MMAP, or just the map hypothesis or the map model. Right, and it's this thing here. Now, because the data is fixed, if we're looking to argmax over a space of models, like a space of weight vectors, we can actually ignore the denominator because it's always the same for every choice of model, and we end up with this thing here. And then, if we assume that either we don't care or we don't know, or that all models are equally likely, then we can actually ignore the prior, and we end up with this thing here, which is the maximum likelihood version. Okay, so there's a very principled way of organizing things if we assume that Bayesian setting. Now, when we want to do classification, we can apply Bayes' theorem, but there's a further step. Now, I have this example. I think most people have seen this kind of example. If you've done AI, you'll have seen this example. So I'll go through it very quickly. It's all about the effect of the prior, right? So there's a bit of data here, a lab test, or the result of a lab test. And there are some priors which are expressed in terms of the prevalence or the rate of prevalence of the disease that you're testing for in the population. Okay, so these are written down as probabilities. Right, so there are two outcomes. And then we have the data, which is a positive test or a negative test, and we can write down these four conditional probabilities in terms of what we would expect to observe in a likelihood sense in terms of so this is the probability of the data given the hypothesis that the patient has the disease. Right, we don't know whether they have the disease. All we have is data on the disease. And if we fill in these values, we can then compute, and we can compute using the MAP formulation. Right? Now in this case, this is MAP, not maximum likelihood, because we have the priors. Right? But the effect of the priors is that we can obtain a result that is consistent with the prior probabilities, although we've actually changed the values. And the most probable hypothesis is still that the patient has cancer, despite some of these probabilities that might, on a naive approach, leave you astray. If you actually calculated the probability, the posterior probability, according to Bayes' theorem, this is not Bayes' theorem, this is MAP. According to Bayes' theorem, the posterior probability has actually increased. All right, which is an interesting observation, but we don't have time to fully get into that. And this is how you do that. Now, for classification, the way to do that in the full Bayesian framework is to define the prior, define the likelihood, which we just did for logistic regression, and then find the parameters by fitting models to data. And then we can classify using the MAP model that we just used. For maximum likelihood, which is what we've been using for linear regression and now logistic regression, we simply define the likelihood, we forget about the prior, and we find the parameters. And then we predict using the maximum likelihood, the set of parameters that is the maximizer for the data given those parameters. So the most probable model given the data is the maximum a posteriori model, that's the MAP model. But we are concerned about classification, and it turns out that this maximum probability model doesn't always give you is not necessarily the most probable classification. So let me just quickly go through a very simple example. Let's say we have three possible models. You can think of them as three different weight vectors for a linear or some classification model. The same data in each case, and we have these probabilities, okay? And now if we've got a new instance, X, we can push through, just as we did for those multiple regression models, the example, each model will give us a classification. These two models give us a negative classification, and the first model gives us a positive classification. And then we ask the question, which is the most probable classification? So probabilities are models, but now we want the probability of the classification. And it turns out that if you work through all of the combinations, it turns out that and here's the Bayes optimal classification, which is find the maximum probability label out of the set of labels Y, given a set of models M. And so you take the probability of the model, which is the this thing here, times the probability of the label given the model, and then you sum all those up. And if you do that for the worked example, it's going to turn out for the two options, positive versus negative, that the negative gives you a more probable classification. So if you act according to this approach, then you get the negative class rather than the positive class. Now, the reason this is useful to know is that this is called the Bayes optimal classification. And it's possible to show that you cannot beat this as a classification method using the same models and the same prior knowledge. The disadvantage is, and the reason that we can't actually use this in practice, is that to do this Bayes optimal, we need to know everything, right? We need to know all of the models, we need to know all of their probabilities given the data, and then we need to know the probability of the classification given the model. And in practice, we don't have that, or we cannot compute that information. But many methods can be viewed as approximating this Bayes optimal classification, particularly things like ensemble methods and various other methods, including neural networks. Okay, so this is really the optimal framework. You can't do it in practice, but you can see that many methods relate to this. And then a similar result, which is a little bit more practical, is the last thing I wanted to show you today. So it's a related idea called the Bayes error. And you will see this, and particularly you will see this when people generate synthetic data where they can know the probability of the class given the data because they set it up like that. They use a data generating function that tells you what that class is given the data. And from this you can derive this Bayes error. And the Bayes error is the best performance attainable by, in this case, a two-class classifier. You can you can work through it for this framework, which we've been using. So what is this? It says the probability of error for classifying some instance x, it's kind of obvious, right? It says the probability of error given x is, well, if the class is the probability of class 1 given x, right? So in general, in real settings, you don't know this, but if you generate the data, you do know this because you generate the class, you generate the data using this probability, this conditional probability. So the error is if you predict class 2, the error is the probability that of class 1 given x, so it's actually class 1, right? So the error would be high in the case if you predict class 2 when the probability of class 1 given x is high. It would be low if the probability of class 1 given x is low, right? So if you do the wrong thing, then the error probability depends on the probability of the thing that you should have done, right? And that's the intuitive idea. And there are two versions, obviously, because you've got two classes. So if you predict the wrong class, your error must be the probability of having done the right thing, okay? Hopefully that makes sense. So that means that the probability of error overall for all x's in some data set is going to be the probability of error given x, this thing here, times the probability of seeing that x. Right? This is just This is just the conditional probability expansion of this, conditional probability expansion of this, summed over all of these. Okay, so this tells you, so how would you use this? Well, you would use this by generating a bunch of data. So you set up first, you might say something like, well, if I will generate data randomly, I will select X values, and then I will define that some rule, if maybe X is greater than 0.5, it's class 1 with probability 0.6 or something like that. Okay, and you generate the data like that, and then you can compare all other algorithms to the Bayes error, right? And it gives you a baseline, right? This is the best you can do. How well do these other algorithms do in terms of getting close to it? Okay, so the other way that this is useful is justifying this decision rule, which is essentially what we've been using, right? We say if the probability of class 1 given X, positive given X, is greater than the probability of class 2 given X, this is essentially logistic regression, but we could even think of other linear classifiers like this, then predict the most probable class, otherwise predict the other class. So it's a very common sense idea and application, but it is a useful way to think about the whole classification problem, because if you knew all these probabilities, then this would be absolutely the best thing that you can do. And the takeaway is, on average, this decision rule minimizes the probability of error of classification error. All right, now, yeah, we're out of time, so let's just summarize. Okay, so what we've talked about this week is classification and learning classifiers. We've talked essentially about classifiers as being a linear model, and we explained the geometric interpretation of that. A classic example of that is perceptron learning. But we also covered logistic regression, which is where you take the linear model and then you apply this additional function, which is like a smooth version of the perceptron threshold function, and make your classification based on a probabilistic argument. So then we looked at maximum likelihood in the context of Bayes, and we established that there were optimal things that you could do in terms of classification, and this will give us the basis to go forward and learn other classification techniques, and we will see how some of these ideas like optimal classification come back in approximations using other algorithms. So that's it. Thanks for your attention. I will write up the rest of the logistic regression classifier derivation using gradient ascent, and hopefully that's convincing. I'll also link to the gradient descent version of that algorithm. And next week we will extend our attention to other versions of algorithms that go beyond this sort of simple parameterization version called non-parametric modeling. Okay, so thanks for your attention. Good to see you. Have a great weekend. See you next time.